Welcome. In a previous video, we've discussed the game of Nim, where there's a pile of 4, a pile of 3, and a pile of 2. Now, you can also play the game of Nim in a more general way. You can have any amount of piles or rows that you like, and you can put however many counters in those piles or rows that you want. And in general, the rules of the game are similar. The player that takes the last counter wins the game, and they alternate removing counters provided that they're all in the same row. Okay, so let's give a formal definition for the game of Nim in general. So in general, if you want to talk about a game of Nim, you can just list a bunch of numbers and one number for each row, just like this example from above. If you have different numbers, it represents different amounts in each row. So if you calculate the Nim sum of these numbers, so if we talk about the Nim sum of 4 and 3 and 3 and 2, and we calculate what that is, well, we're going to give a formal name to that. We're going to call that the Nim sum of the game. So the 4, 3, 2 itself represents a position in the game, where the 4, 3, 2, when Nim sum together, gives you the Nim sum of the game. And that's exactly what we put in the definition below. So the Nim sum of the game is the Nim sum of those numbers. Now there's a couple of lemmas that are going to be really helpful for figuring out a winning strategy to the game of Nim. We're not going to go through the proofs of these lemmas. If you'd like to on your own, you can read closely what those proofs are. The real important thing that we're going to highlight in this video is what the lemmas say. So the first lemma that we're going to dig into here says that every move in the game of Nim will change the Nim sum. So whatever number this is, if you make a valid move in the game, if it's like 7 to begin with, and you make some valid move, then it has to change. It'll be something other than what it was before. So let's put that into practice. Let's collect these definitions and try this lemma out. So in the next example, we're considering a game of Nim, and it first asks us to use the definition above to represent the state, or position if you like, of this game of Nim, and in terms of the starting position. So this is just a list of numbers. So we have a row of 5, a row of 4, and a row of 3. And we're going to again keep with the standard of larger numbers on the left-hand side, just so we don't have any confusion about repeating symmetric positions. So then there's the Nim sum of the game as we defined above. So that is calculating 5, Nim summed with 4, Nim summed with 3. So 5 is 4 plus 1, Nim summed with 4, and Nim summed with 2 plus 1. So we look for any pairs to cancel out. We see 2 1s and 2 4s. There's just a 2 left over. So that is the Nim sum of our game. Okay, so finally, to finish this example off, we're going to make any move and notice that the Nim sum of the game will change. So right now, the Nim sum of the game is 2. We're going to make a move and it's going to change. I'm going to challenge you to do that on your own. I want you to play this game, make a move, whatever you want, to this game board, taking whatever you want from one particular row, and then calculate the Nim sum again, and I can guarantee you ahead of time that you are not going to get 2. I don't know what you're going to get, but I do know that it won't be 2. So pause now and give that a try. I'll do it on my own as well. Okay, so I've decided to take 4 from the last row and get the 4, 3, 1 position. So there's now a row of 4 and a row of 3 and a row of 1. So I'll take the Nim sum of this and see what we get. So 4 Nim sums with 3, which changes to 2 plus 1. And 1 is already a power of 2, 2 to the power 0, so we'll leave that as 1. We cross out anything that we see twice, and we add up what's left, and we get 6. And we notice, indeed, that number did change. Also notice that there's not really an association with bigger or smaller when you're nim summing, as there is with regular summing. If you're just adding numbers, you're adding positive numbers, things get bigger. When you're nim summing different combinations together, things could get bigger or smaller. There's no real rule in that direction. So it's kind of nice to let go of what's big and what's small when you're just looking at an expression with nim sums. Okay, so the next lemma that we want to discuss. So we just discussed that when we make a move, the nim sum changes. This next lemma says that there's always a move that changes the nim sum with a non-zero sum to a zero sum. So if you have something like 2 in your nim sum, you can change that to 0. There is a move that does that for you. If you have 7, something other than 0, you can change it to 0, and so on. So we're not going to go through the proof, but if you are interested in the details below, you can pause the video now and check that out. We're going to work with the statement that the lemma gives us. So in the example below, let's try to think about that. So in this game, the nim sum is not 0. We actually calculated the nim sum of that game earlier on and found that it was 2. So our job is to take this game that we're looking at now, which has a nim sum of 2, and change that by making a valid move in the game to 0. We want to change that 2 to a 0. And the lemma that we just read told us that there should be a way to do this. There should be a way to change any non-zero nim sum to 0. So we're going to try to find such a move. Now, because these numbers are relatively small, it's not too tricky to find this. In other cases, when these numbers get bigger and more complicated, we're going to go through a step-by-step process later on that will tell us how to deal with those situations. For now, we're just going to do a little bit of guessing and testing to see if we can figure it out. So can you think of a move to make here that would create a new position in the game of nim that would make the game have a nim sum of 0? See if you can do that. Pause now, give it a try. Okay, so maybe you noticed that in this calculation, if that 2 wasn't there, we would cancel everything out and we'd end up getting a 0. So if we take this 2 away, that would correspond to the move that takes 2 from the very first row. That's the move that we want to make. So now we would calculate the nim sum of 5, 4, and 1, and we would get 4 plus 1, nim summed with 4, nim summed with 1, and everything kindly cancels out for us, and we get 0 left over. So the old nim sum was 2, and the new nim sum, as desired, is 0. All right, so now we get to put the two lemmas together and build a theorem. If you've never heard the sequence of lemma and then theorem, the idea is that lemmas are a more basic result or something that comes before a theorem, and then the theorem is something that mathematicians are jumping up and down about. We're all excited. This is the big result that we've been waiting for. So here it comes. The game of nim is in a hot position if and only if the nim sum is something other than 0. So if the nim sum is 5, it's a hot position. If the nim sum is 20, it's a hot position. If the nim sum is 0, the statement says if and only if. So if it's 0, then it's not a hot position, it's a cold position. Okay, so how can we prove this statement? This proof we will go through. This is an important one. So suppose that the game starts with a non-zero nim sum. What can the first player do? Well, we just learned that the first player can always change the nim sum to 0. So the first player moves so the new nim sum is 0. That's their job. And that was described in lemma 3, saying that we'd always be allowed to do that. And then the second player will have to move, of course, and they're going to move when the game has a nim sum of 0. And let's remember back to Lemma 2. Lemma 2 said the game has to change its nim sum as you play it. So player 2 is forced to move so that the nim sum is no longer 0. It was 0 to begin with, and now it's no longer 0. Then rinse and repeat. The first player changes it back to 0. The next player, second player, changes it away from 0. And so on and so on. So this process continues. Eventually the game will end, right? This is a finite game and there's only so many counters, and eventually we run out of the counters that are on the table in front of us. Which player is going to move so that there's no counters left in front of you? Well, eventually the first player will move so that there's no counters left, and it's the first player this whole time that has been moving so that the nim sum is 0. So it's the first player that is going to be the one that makes sure that the game ends with no counters, and the first player will win because the game is described as the player that picks up the last counter or last bunch of counters all at once wins the game. So this doesn't mean that the first player always wins these style of games. The second player, of course, can steal this strategy if the game starts with a nim sum of 0. Then it would be the first player that would be forced to move away from 0, and the second player can take over the winning strategy. So that's where the if and only if is coming from. So how about we put this into practice? Let's go back to the very first game that we played, and we analyzed it with a state diagram. There's a 4-3-2 game. And let's try to see how this theorem fits in with that state diagram. Okay, so here's a state diagram of the 4-3-2 game. What I'd like you to do is go through all the positions that are in this diagram and assign them their nim sum. So right next to the position, just write whatever the nim sum is. So this nim sum here is 0. So go ahead and pause the video, do that as an activity before the answer comes up on the screen. Okay, so all of our nim sums are assigned. And if we think back to the theorem that we were just talking about, the game starts with a non-zero nim sum. So that would make sense that this is a hot position. There's a way to change it all to 0. So our new nim sum is 0. That's a cold position. Every way of playing from there gives us hot positions, and those are all non-zero nim sums. We change those positions into 0, and from there you must play into hot positions, and then from there you must play into cold positions, which are 0, and then finally you must finish off at the cold position, which is a 0. So it backs up what the theorem was saying in terms of these nim sums. And also, if you think back to this diagram to begin with, I suppose this is just a partial state diagram. There's many other ways of playing from here. How could someone know that this move was a good move? Well, if you know about the nim sum ahead of time, you can make a diagram like this and make the correct first move. So I knew ahead of time that that was a good first move to make, and I didn't think about all of the other options. Okay, so next we're going to discuss how to come up with the correct move to make, other than just a guess and test method. Okay, so now we're going to discuss something that comes after a theorem, often called that a corollary. It's kind of something that trickles out of a theorem, another result that we get almost for free by just maybe looking at the proof or looking at the result. So lemmas come before theorems and corollaries come after theorems. So there's a 3-step program here to dealing with how to find the correct move to make in a game of Nim. So how do we change a non-zero Nim sum to 0? So the first thing that you do is calculate the Nim sum. So this is some number, we're going to call it S. And every time you have a number, you can break it into powers of 2. and then we note the largest power of 2 that appears in that list. So we've maybe ordered these powers of 2, where k is the biggest one, and then the t's that come after that are smaller. Let's do that step below. Okay, so our first step is to find the Nim Sum. So I want to know what number this s is. To find the s, I need to calculate that. And to calculate that Nim Sum that's sitting there, we need to follow the rules and break this up into different powers of 2. 8 and 16 are already powers of 2. 5 changes into 4 plus 1. And then we cancel out anything to be canceled. This time there's nothing to cancel at this point. There's no pairs. Often there is. This time there isn't. That's okay. So we add up what's left to get 29. So now that we've found this number s right here, we're interested in what does it equal in terms of a bunch of different powers of 2. Let's write that on the next line. So this means that my number s, which we found is equal to 29, which equals 16 plus 8 plus 4 plus 1. What we want to know is what is the highest power of 2 in the number 29. That's why we wrote out all these. So that highest power that we're looking for is 16. So something to kind of watch out for here is in this calculation, there wasn't any canceling out. But even if there was, like if there was like a 32 Nim summed with a 32 in the calculation, you still got 29 left over as the result of the Nim sum, because the 32s would cancel out. The point of my display here is that 32 is not the largest power of 2. It may have occurred in the calculation to arrive at what that Nim sum is, but if you crossed out bigger powers of 2, then they're not the power of 2 that you notice here. You take the number, you write it out as a bunch of powers of 2, and then you find the largest one. So the 2 to the k that we're interested in is 2 to the power 4 or 16. Okay, let's move on to step 2. So in step 2, it says find a row that 2 to the power k appears in. So when we say find a row with a sub I and it equals a bunch of powers of 2 and one of them is the power of 2 that we found above, each of these a sub i's are the rows. So row 1 is a sub 1, and there's 5 in that row, so that number happens to be 5. A sub 2 is referring to the second row, and that number happens to be 8. And a sub 3 is referring to the last row, and that number happens to be 16. So we get to look at all of these numbers, 5, 8, and 16, and think about where our highest power is appearing in those numbers. It could appear in more than one number. It could appear in all 3 of these numbers, and then you would have a choice from here on. In this case, for this example, 16 is only in the number 16 appearing as a power of 2, so you have to pick 3 as your choice. So find a row. For our purposes, for this example below, it would be row 3. I would equal 3, and a sub I would equal 16. So in step 2, we pick row 3. So our final step is going to be to leave a certain number of counters in that row. So in step 2, we decided, okay, now we're going to play the game by operating on row 3. So row 3 has 16 counters. That's our a sub I. And we're going to nim sum that with the nim sum itself. So we need to calculate this number. So a sub I is 16, and we nim sum that with the Nim Sum. We Nim Sum it with S. Let's remember what S is. We calculated S to be 29. So 16 Nim Summed with 29. Need to write out our powers of 2. 16 is a power of 2, and then 29 is 16 plus 8 plus 4 plus 1. So our 16 cancels out, and we're left with 8 plus 4 plus 1. So our number is 13. Now let's remember, this is how many you leave in the last row, not how many you take. It says leave 13 counters in row 3. That's what we need to write down. Maybe we'll write it down in terms of the move that we make. There's 16 to begin with. We take 3. And so once again, in review, because we found that the Nim Sum was non-zero right away, we knew that the first player can always win, and the move that they make is stated below. So the first player can always win by taking 3 from row 3. Let's do one more example. Okay, so in this example, we've got a bunch of rows and some counters. Once again, the very first thing that we want to do is find the Nim Sum. Okay, so we've written down the amounts in each row. So now we'll calculate our Nim Sum by breaking up into different powers of 2. So 2 and 3 is 2 plus 1. And 5 is 4 plus 1. And copy 8, it's a power of 2. And then 13 would be 8 plus 4 plus 1. Okay, now we get to cancel out pairs. So 2 1s cancel out, 2 2s cancel out, 2 4s cancel out, 2 1s cancel out, and 2 8s cancel out. So there's nothing left over. We have 0. In this case, we don't need to analyze a first move of the game. The first move is kind of trivial. The first player would just play and change the Nim Sum to something other than 0, and the second player can always win. Okay, so that summarizes how to always win the game of Nim and what correct move that you can make in a systematic way to change the game from hot to cold, or in other words, from non-zero to 0. In the next video, we're going to discuss a variation of Nim called classic Nim. So in regular Nim, you take the last counter to win the game. There's going to be one switch up of the rules for classic Nim. When you take the last counter in classic Nim, you lose the game, but the rest of the rules will be the same. So maybe before you start watching the next video, you might want to think about that variation. Thanks so much for listening. We'll see you on the next one.